Somewhere above Saturn's north pole, an aurora has been quietly running a hidden engine for decades, one that scientists just proved is powerful enough to make an entire planet appear to change its own rotation speed. Stick around, because I'm going to walk you through exactly what NASA just confirmed about Saturn using the James Webb Space Telescope. And trust me, some of this is stranger than anything a headline can really capture. And if you like getting these stories from real published research instead of recycled clickbait, go ahead and subscribe now because there's a lot more of this coming. Let's start with a mystery that quietly frustrated scientists for more than 2 decades, because understanding how strange this puzzle really was makes the solution land a lot harder. Back in 2004, NASA's Cassini spacecraft arrived at Saturn and began one of the most detailed studies of a planet ever attempted, staying in orbit for 13 years before its mission finally ended in 2017. Almost immediately, researchers ran into something that made no physical sense. Every planet has a rotation rate, the actual speed, at which the solid or fluid body underneath spins on its axis. For gas giants like Saturn, scientists typically estimate that rate by tracking radio signals tied to the planet's magnetic field, since there's no solid surface to watch directly. When Cassini measured Saturn's radio-based rotation period, the number kept drifting, not by a huge amount, but enough that it genuinely looked like the entire planet was gradually speeding up or slowing down over time. That's not something planets are supposed to do on short timescales. A gas giant's rotation is essentially locked in from its formation, and nothing about basic planetary physics allows it to casually shift its spin rate year over year. For a while, scientists were stuck. The data was clearly showing something real, but nobody could explain what was actually driving it. The first real breakthrough came in 2021, when a research team led by Professor Tom Stallard at Northumbria University proposed a different way of thinking about the entire problem. Saturn's spin itself, they argued, probably wasn't changing at all. Instead, the signal scientists were using to measure it, the electrical activity linked to Saturn's aurora, was being distorted by winds high up in the planet's atmosphere. Those winds were interfering with the readings, making it look like the whole planet was speeding up and slowing down when in reality the measurement itself was just being thrown off. That explained why the numbers were misleading, but it left an even bigger question sitting right behind it. What was actually generating those atmospheric winds in the first place? For years, that question stayed open because no instrument available at the time had the sensitivity to map Saturn's upper atmosphere in enough detail to find out. That's where the James Webb Space Telescope finally stepped in. Unlike Cassini, which physically orbited Saturn and could only observe it from up close for a limited window, Webb studies Saturn from roughly 900 million miles away, using instruments precise enough to read incredibly faint details in reflected light without ever needing to leave Earth's orbit. To crack this specific mystery, Stallard's team pointed Webb directly at Saturn's northern auroral region and kept watching continuously for an entire Saturnian day, capturing a level of detail no previous telescope had ever been able to produce. Specifically, they focused on faint infrared light given off by a molecule called trihydrogen cation, a charged particle that forms naturally in Saturn's upper atmosphere and acts almost like a built-in thermometer, glowing differently depending on the temperature around it. By carefully mapping that glow across the entire auroral region, the team produced the most detailed temperature and particle density maps of Saturn's upper atmosphere ever created. Here's where the improvement becomes genuinely staggering. Earlier measurement techniques carried an uncertainty of roughly 50 degrees Celsius, which is a huge margin of error when you're trying to detect subtle temperature variations. Webb's observations came back roughly 10 times more precise than that, finally allowing researchers to isolate specific patterns of heating and cooling across small regions of the atmosphere instead of just a single averaged number. And when they compared this new data against computer models that had been sitting untested for more than a decade, everything clicked into place, but only under one very specific condition. The models only work correctly if the source of the atmospheric heating was located exactly where the strongest auroral particles were entering Saturn's atmosphere. And what that data revealed is that Saturn's aurora isn't just a dazzling light show happening at the poles for no functional reason. It's actively powering a self-sustaining feedback loop. Energy from the aurora heats a specific region of the upper atmosphere. That localized heating generates winds. Those winds then produce electrical currents, and those electrical currents, in turn, help power the aurora itself, which continues heating the atmosphere and keeping the entire cycle running continuously. Researchers are now describing it essentially as a planetary heat pump, a closed loop where each part of the process feeds directly into the next one, quietly sustaining itself for as long as anyone has been watching. That decades-old mystery about Saturn's rotation, speeding up and slowing down, wasn't ever about the planet's actual spin changing at all. It was the signature of this self-powering atmospheric engine quietly distorting the readings the entire time. If you're the kind of person who finds it wild that a planet's own aurora can trick scientists into thinking the whole world is changing speed, drop a like on this video, because that's honestly one of the stranger feedback loops confirmed anywhere in the solar system. And the implications reach further than just Saturn. Researchers found direct evidence that Saturn's atmosphere and its magnetosphere, the enormous region of space shaped by the planet's magnetic field, are tightly linked together, constantly exchanging energy back and forth in both directions. That kind of connection helps explain why this cycle has stayed stable for so long, and scientists suspect similar interactions might be happening quietly on other planets too, places where nobody has yet had an instrument sensitive enough to detect them. In other words, solving one very specific 20-year-old Saturn mystery may have just handed researchers a blueprint for finding hidden atmospheric engines running on completely different worlds. That wasn't the only major Saturn result to come out around the same stretch of time either. Just a few months earlier, in March of 2026, NASA released what's being called the most detailed combined view of Saturn ever produced, pairing new infrared images from Webb with visible light images from the Hubble Space Telescope, taken about 14 weeks apart in late 2024. And the reason scientists paired these two telescopes together rather than relying on just one comes down to a simple but powerful idea. Hubble sees Saturn the way our eyes basically would, picking up on subtle color variations across its cloud bands. Webb, on the other hand, sees Saturn in infrared, which lets it sense clouds and chemical layers sitting at completely different depths in the atmosphere, from the deep, dense cloud layers all the way up to the thin, tenuous outer atmosphere. Combining both views lets researchers essentially slice through Saturn's atmosphere the way you'd peel back layers of an onion, building a three-dimensional picture of how the entire system behaves, instead of just a flat snapshot. The details visible in these combined images are genuinely remarkable once you know what you're looking at. In the Webb infrared image, there's a long-lived jet stream nicknamed the ribbon wave, snaking across Saturn's northern mid-latitudes, shaped by atmospheric waves that are otherwise completely invisible to normal observation. Just below it sits a small lingering remnant of what scientists call the Great Springtime Storm, a massive storm system that first erupted on Saturn between 2010 and 2012, and whose faint traces are apparently still detectable well over a decade later. Several additional storm systems are scattered across Saturn's southern hemisphere in the same image, all shaped by powerful winds and pressure systems churning beneath the visible cloud tops, which is part of why scientists treat Saturn as a kind of natural laboratory for studying extreme fluid dynamics that would be impossible to recreate here on Earth. There's also Saturn's famous hexagon, a six-sided jet stream pattern wrapping around the planet's north pole that was first discovered by NASA's Voyager spacecraft all the way back in 1981. Both the Webb and Hubble images from this pairing faintly capture its pointed edges, and researchers note this stability is worth appreciating. On its own, since a weather pattern holding a geometric hexagonal shape for more than 4 decades straight is not something you'd expect from ordinary atmospheric turbulence. And there's a bit of urgency tied to these particular observations too. As Saturn's orbit slowly carries its north pole toward winter darkness, researchers expect this could be one of the last high-resolution looks at the hexagon that anyone gets for years, since that region of the planet is about to shift into roughly a decade and a half of darkness, before sunlight returns to illuminate it clearly again. One especially strange detail shows up specifically in Webb's infrared data. Saturn's poles appear distinctly gray-green in these images, glowing at a particular infrared wavelength that scientists are still working to fully explain. One possibility is that it comes from a layer of high-altitude particles scattering light differently at those latitudes than anywhere else on the planet. The other leading explanation ties directly back to Saturn's auroral activity, the same underlying phenomenon behind the rotation mystery, where charged particles interacting with the planet's magnetic field produce a faint glow concentrated near the poles. Either way, it's yet another small, previously unnoticed detail that only became visible once an instrument as sensitive as Webb finally got a clear look. Even Saturn's rings behave differently depending on which telescope is watching them. In Webb's infrared view, the rings appear extremely bright, almost glowing, because they're made largely of highly reflective water ice that lights up strongly at infrared wavelengths. In Hubble's visible light image, the same rings appear noticeably dimmer by comparison. Subtle structural features inside the rings, including transient spoke-like patterns and internal banding within the dense central B ring, show up differently across the two datasets as well, giving researchers effectively two separate perspectives on the same structure that, together, provide details neither telescope could capture completely on its own. And it's worth remembering that Webb isn't limited to studying Saturn's atmosphere and rings. It's also been turning its instruments towards Saturn's largest moon, Titan, a world with its own thick, hazy atmosphere and complete weather system. built not out of water, but out of liquid methane. Earlier Webb observations of Titan confirmed patterns of cloud cover and seasonal methane weather shifting across the moon's surface, essentially giving scientists a working forecast for a world where it can, quite literally, rain flammable liquid hydrocarbons out of the sky. Combined with everything Webb and Hubble have now confirmed about Saturn itself, the picture emerging is one of an entire planetary system, storms, jet streams, poles, rings, and moons that's continuously interacting in ways scientists are only now able to observe clearly enough to properly study. Step back and look at what's actually been achieved here, because it's easy to breeze past just how significant this is. A rotation mystery that stumped scientists using one of the most sophisticated planetary orbiters ever built, sitting right next to Saturn for 13 straight years, finally got solved using a telescope, studying the planet from roughly 900 million miles away. That's not a small technical footnote. That's a demonstration of just how far infrared observation technology has come, allowing researchers to resolve details in Saturn's upper atmosphere with a level of precision that direct spacecraft measurements alone couldn't fully achieve. And this is very likely just the beginning. Webb continues to observe Saturn periodically as part of ongoing monitoring efforts, adding new data points to a scientific record that already spans Cassini's 13 years in orbit and Hubble's multi-decade Opal monitoring program, tracking all of the outer planet's atmospheres year after year. What makes Saturn specifically worth this level of attention isn't just that it looks visually striking with its rings, although it certainly does. It's that Saturn functions as an active, constantly shifting natural laboratory, one where scientists can study extreme winds, self-sustaining electrical and thermal feedback loops, ring dynamics, and moon weather systems, all within a single, relatively nearby target that keeps producing new surprises the longer researchers keep watching. Every time Webb turns its instruments back toward Saturn, it isn't simply capturing another pretty picture for the archives. It's adding another data point to an ongoing scientific investigation into how an entire planetary system holds itself together, and after this year, we now know that at least part of the answer involves the planet's own aurora, quietly running an engine that keeps the whole upper atmosphere in motion, all on its own, without any outside push required at all. If stories like this one, built entirely from real published research instead of exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because Webb is still watching Saturn closely, and there's a good chance the next round of observations reveals something just as strange as what we covered today. Thanks for watching, and I will see you in the next one.